Hey guys, so welcome back. In this video, we'll be trying to solve the problem Sudoku Solver in Leetcode. Okay, it's a hard problem and it has also been asked in many interviews for companies such as Microsoft and Google. All right, so write a program to solve a Sudoku puzzle by filling the empty cells. Okay, a Sudoku solution must satisfy all of the following rules. Now, those of you who play Sudoku, you might already know the rules, right? That is, no number can be repeated on the same row, column, or any of the sub boxes or sub squares. Okay, and in our question, an empty space will be represented by a dot character. Okay, it will be a dot. So here we go. Our board will be in the form of a 9 by 9 matrix. Okay, and empty spaces will be represented by the dot character. Okay, we are basically supposed to solve this board in the most efficient way. Okay, so now let's see as to how we can solve this. So I have a Sudoku board right here. Okay, I have a sample board right here. Now, as you all know, there are many solutions to this. Now let's go across the naive solution to solve this. Okay, like we'll just think of as to how a beginner will solve this. Now, what you could do is like the easiest solution is basically to put every single number in every single square and check for the solution. Okay, so basically what I mean by that is I have my first empty square over here. I will insert every single number. I'll insert 1, then 2, 3, 4, 5, all the way up till 9. I will insert every single number. Similarly, I'll do the exact same thing for every other square. Okay, and in that way, like you can actually find the answer. But the issue is that it is not at all efficient. Why? Because a Sudoku board has 9 rows and 9 columns. Okay, so let's say in the worst case, everything is empty. Okay, so it has 81 squares. It has 81 squares. All right, and in each of these squares, there are 9 possibilities of numbers which can go into it, right? Anywhere from 1 to 9. So you have 9 possibilities for each square and you have 81 squares. So basically your runtime will be in the order of 9 raised to 81. Now that is a massive number, right? Like it's a very, very big number. Now that is literally very inefficient and even your computer will take ages to solve it. Okay, so we have to think of a more efficient solution to this, right? So here is where we will use a solution that involves backtracking and recursion. Okay, so for this solution, I have a few functions. Okay, my first function will be called empty. Okay, now I'll be explaining this as I go by. Okay, now empty will basically be in charge of finding empty squares. Okay, because we can fill our numbers only in empty squares, right? So this empty function will find out our empty squares for us, like this one, this one, this one, this one, and so on. Okay, our second function will be called isValid. Now this function will basically be used to check the validity of our number. Basically, it will just check if our numbers or if the number we're adding right now, if it follows the rules of Sudoku or not. I'll just write here verifies rules. Okay, I'll be explaining what I mean by all this. Now our last function will be our main solver function, which will implement recursion and backtracking to solve it. Okay, so again, first I will go to the empty. I'll call the empty function. Okay, we found our first empty square over here. Okay, now we'll try to insert numbers all the way from 1 up till 9. Okay, we'll start with 1. Now we'll call the isValid function to check if 1 is a valid insertion. Right, so we'll try to input 1. Is this valid? It's actually not valid. Why? If you see, 1 is being repeated on the same row. The rules say that a number cannot be repeated on the same row, column, or any of the subsquares, right? Now 1 is being repeated on the same row. So 1 is not a valid insertion. Now we'll insert 2. And now we'll check if this is valid, right? Now 2 is valid. Why? Because 2 is not anywhere there on the same row. It is not there in this row. It is also not there in this column. It is also not there in this subsquare, right? So 2 is a valid entry. Now we'll again move forward and find the next empty square, right? Here, let us aim for, let's see, We'll again start from 1. Again, 1 can't be inserted. It's being repeated on the same row. We'll insert 2. Even 2 can't be inserted here because again 2 is already existent in the same row. We'll again go forward. 3 also can't be inserted because it is again repeating on the same row. Let's check for 4. 4 also can't be inserted. It is repeating on the same row. Right. Now we'll check 5. Now 5 is not being repeated on this entire row, this entire column, or in the subsquare, right? 5 is not being repeated anywhere. So we can insert 5. Now we'll move on to the next square. We'll again check for 1, can't insert 2, 3, 4, 5. It's like we can't insert any of those. Right now we'll insert from 6. We'll see, can we insert 6 here? Yes, we can insert 6 because 6 is not being repeated in this column, in this row, or in the subsquare, right? 6 is not being repeated anywhere. So we can insert 6. All right, now let's move forward. We'll again try to insert 1, 2, 3, 4, 5, 6. Cannot be inserted here. We'll check with 7. Can we insert 7 here? Yes, we can insert, we cannot insert 7 because 7 is being repeated in the same row. Okay, now we'll check for 8. Can we insert 8 here? No, we can't insert 8 because 8 is being repeated in the same column. Now we go to our last possibility, which is 9. Can we insert 9 here? We cannot insert 9 because 9 is again coming on the same row. Now we have run out of options, right? When we reach 9, we attempted to insert every number into this, but none of them are valid insertions. So what do? We use recursion and we backtrack to the last number. Now, because this last number is here, we have no possible insertions over here, right? So now from this number, we move forward. Now instead of 6, we'll try to insert 7. Can we insert 7 here? No, we can't. It's being repeated. Can we insert 8? Again, can't. It's being repeated. Can we insert 9? Again, no. It's being repeated. So what do? We backtrack again over here. Now we'll reach 5. Right. Now we'll try to change this. Now from 5, we'll go to 6. Can we insert 6 here? Yes, we can insert 6, right? We can insert 6 here. Like it's not there on the same row, column, or subsquare. Now we'll again move forward. Over here, we can't insert 1, 2, 3, or 4. We can't insert 5 because 5 is here. We can't insert 6. We can't insert 7 also over here because 7 is on the same row. We can't insert 8. And we can't insert 9, right? Again, we'll backtrack, okay? We'll backtrack and we'll go to 7 here. Can we insert 7? No, we can't insert 7. It's being repeated. Then we'll move on to 8. We can insert 8, right? Like it's not being repeated. Over here, again, means we can't insert 1, 2, 3, or 4. Can we insert 5? No, we can't insert 5 because 5 is over here. Can we insert 6? Yes, we can insert 6. So 6 will come here. Right. Then again, we'll move forward. Again, we'll check 1, 2, 3, 4, 5, 6, 7. Now, this is basically the approach that we follow, right? If we don't find a valid solution, we will just backtrack one step back and change our existing solution. So at the end, we'll finally reach a solution for this board. Right now, that is a basic approach. Okay, now like this might seem a bit vague, but while coding the solution out, I'll just explain everything in as much detail as I can. Okay, so now let's go and code the solution out. Okay, so let's start. As I said, we need a function for checking the empty squares, right? So what we'll do is we'll make a function for that. Def empty, it'll take the board in as an argument, right? For I in range 9, because we have 9 rows and we also have 9 columns. So for j in range 9, okay? Now what we'll do is, how do we find an empty square? Here they said that empty cells are represented by the dot character, right? So I'll just do if board of ij is equal to a dot, then it means that it's empty, right? So I'll return the indexes of the empty square. So I'll just do I, comma j. We'll return this, okay? At the end, if there is no empty square, which means that if the board is solved, because only if the board is solved will you have no other empty squares, right? I'll just return none, okay, at the end. Now, easy so far, right? This function is for finding the empty squares. Now let's make a function for checking if it is valid, okay? Def is valid. We'll take the board in as an argument. We'll take a number, which is the number we want to check if it is valid or not. And we'll take index. Now, index is basically this thing right here, right? Like the index of the empty square. We'll take that also. All right. Now, inside this function, what we do? First of all, we have to check if it repeats on the same row, right? So for that, for I in range, again, we'll go up till 9. Okay. Now, if board of index 0 and I. Now, it's important that you guys understand what this is for. Now, index 0, which is the empty square's x coordinate. Okay. So we'll check if the x coordinate of that and I is empty or not. Okay, so I'll just be explaining this on my board real quick. Okay, so say for example, we find an empty square over here. Okay, we found an empty square over here. Now, what is the index of this empty square? The index is what? Which row is it? 0, 1, 2, 3, 4, 5. It is the 5th row, right? So I will be 5. What is the column number? 0, 1, 2, 3, 4, 5. Even the column number is 5, right? So this is the x and y coordinates of our empty square. Okay. Now, say for example, in the empty square, we were to insert a number called 1, for example. Now, we have to first check this entire row, right? So as I said, for that, we will check if board of the first index of our empty square or the x index of our empty square, 5 of I is equal to the number we want to insert or not. So here, if we want to insert 1, we'll check this entire row for 1, right? Because it should not be existent. So board of 5 of I is what? 5 is a row. So 0, 1, 2, 3, 4, 5. We'll check 5, 0, 5, 1. So we'll check 5, 0, which is here. 5, 1, 5, 2. We'll go all the way up till 5, 8 and check if 1 is there, right? And if 1 is there, it basically means that the number is being repeated, right? So 1 cannot be a valid insertion. Now, while we go across this entire row, we'll also go across our current square 5, 5, which has 1 inside of it, right? So it should not count this 1 which we inserted just now as a duplicate 1, right? So what we'll do is we'll just make a condition that index, right? Index of 1 should not be equal to I. Should not be equal to I. Now, index of 1 is basically the y coordinate of our empty square. Now, this coordinate and this coordinate should never be same, right? Because if y is same as I, it basically means that we reach the square where we want to insert our element, right? So we'll just not consider that. All right. So hopefully you guys understood. So now over here, if board index 0 of I is equal to num, and what should we do? Index of 1 not equal to I, right? So we don't count the current element which we inserted. We can just return false. All right. Now we'll do this exact same thing for the column. All right. So I'll just copy this. For the column also, we'll do the exact same thing. The only change being is that now we'll just put I here and we'll put index of 1 here because we want to check each column. And over here, it'll be index 0 should not be equal to I. Now you guys can verify this using this exact same method which I showed, like which I showed for row, but you can apply the same thing for the column as well. Okay, now here we checked if any number is being repeated in the row or column. Now we have to check if it's repeating in this subsquare, right? We have these subsquares here. Now, how many subsquares do we have? How many subsquares do we have? Let me just remove all this first. All right. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 subsquares, right? So first we have to find out in which subsquare our element is. Okay. Now I want to insert an element over here. Now this is in our what? 0, 1, 2, 3, 4. It's in our 4 subsquare, right? So how do we find that? Again, first of all, the index of this empty square, what is it? It is 5, comma 5. Now all we do is that we'll basically do x coordinate float division by 3. We'll do the exact same thing for the y coordinate, and that will inform us as to which subsquare we are. So if you do 5 floor division by 3, your answer will be 1, right? Your answer will be 1. Even for y, if you do 5 floor division by 3, your answer will again be 1. Now this basically means we are in the subsquare at 1 comma 1, right? If you see 1, the first row, so 0, 1, like we are in the first row over here. Again, we are following 0 based indexing, okay? So 1 comma 1 is basically this subsquare right here, right? So it makes sure, or like it basically informs us as to which subsquare we have to check. Okay, it's 1 comma 1. Now basically what we do here is that, right, we will multiply. Okay, like first I'll do this, so I'll just explain along the way. Okay, so it's a bit easier. So now what I'll do is that I'll just do index 1, right, to find the index of the subsquare. Index 1 is basically equal to index of 0 floor division by 3. Same thing for index 2. Index 2 is equal to index of 1 floor division by 3. All right. Now what I'll do is that for I in range, index 1 will start from that point, or no, we'll start from index 1 into 3 to index 1 into 3 plus 3. I'll be explaining as to why we are doing this. Okay, if we go back, our index is 1. Okay, so we are basically starting from 1 into 3, which is 3, and we are going up till 1 into 3 plus 3, which is going to be 6. All right, like of course, means like it won't go up till 6, it'll go only up till 5 because it's a for loop, right? Like it won't go up till the last element. So we'll go from 3 to 5. If you see, that is the exact range we have to cover, right? 0, 1, 2, 3. It's over here. We'll check index 3, index 4, index 5. See, this is basically how we check each subsquare. Now we'll also use J loop with this. So we'll also check this square, we'll check this square, and we'll check this square. Then similarly, we'll check this square, and this square. Again, this square is a square in which we are inserting. So we should not check this particular square. We'll make an exception for that. Okay. So hopefully you guys understood the logic here. Right. Now again, for J in range, right, I'll just copy this. I want to waste time. Over here, instead of index 1, I'll just do index 2. All right. Let's move down a bit. Now over here, what should we check? Right, what should we check? If board of I and J is equal to num, right, and I comma J is not equal to index. This is basically to ensure that the small square in which we are going through is not the square in which we inserted right now, right? Because we don't want to consider that square. If it is so, we can again return false. Now, if none of these things return false, at the end we can just return true. All right. Up till here, hopefully all of you understood. This is outside the function. Oops. Put it inside. Okay. Now we'll do our main function. Now this is a solver function. This might also be the most confusing for some people. Okay. You're just supposed to make sure that you understand the basics of recursion. Okay. Now I'll just do here def solver. It'll take the board in as an argument. Okay. Now, again, as I mentioned earlier while doing this empty function, if there is no empty spaces, it basically means that the board is solved, because say for example, we insert numbers into all the squares up till the end. There will be no more empty squares, right? So if there are no empty squares, it means that the board is solved, right? So we'll just do that small condition first. If not empty, now this will be our base case. All of you know is that like there will be a base case for recursion, right? So if not empty of board, so we'll basically call the empty function and check, right, if it's empty or not. If it is not empty, I'll just return true, which means that the board is solved. Okay, as simple as that. Else, now if there are spaces, first thing is we have to get the indexes, right? So I'll just do raw comma col is equal to empty board. Now this will basically give us the indexes of the empty squares inside the board. Okay, simple enough. Now I'll do a for loop because we have to insert numbers from 1 to 9. So for I in range, we have to insert from 1 to 9. So I'll do 1 comma 10. Okay. Now inside of this, before we insert, what should we do? We should check if the number is valid or not. So if is valid, the arguments were what again? Argument was board, number and index. Okay, board is here. Number is the number which we're inserting now, which will be I, right? And index. Now index will basically be row and column, right? So I'll just do row comma col. Okay, now this it'll call the is valid function, and this function will basically check as to the insertion we want to do, if it is right or wrong. Okay, if it is right, what do? We will insert this into the board, right? So I'll just do board row col is equal to string of I. Remember, over here they want it in the string format, okay, like it's not in the number format. So you basically convert the integer into a string and you insert it. All right, now here I will be writing if solver board return true. I'll be explaining what this means. All right, let me first code this out. Then I'll just do board row column equal to 0, and at the end return true. Okay, now sorry, not 0, it should be a dot because we represent empty characters as dots. Okay, so I'll now be explaining this portion in a bit more detail. Okay, now we take a number. Okay, we check if it's a valid number. If it's a valid number, we insert the number into the board. Okay, now after we insert the number into the board, we will call the solver function again recursively, right? Because as I said, after we insert in one number, so I'll just take my board over here. Now say for example over here, as I said, here the input should be 2. After I insert this here, I have to go to the next input, right? So I'll call the function recursively. So I'll again go to the next square, see for the input, then next square, then next square. It's like we want to keep on going up till the next square until we find the answer. Okay, so now this solver function will call the solver function repeatedly, right? Or like recursively. Now we'll again go to the solver function. We'll check all these conditions and we'll go down. Now, as I said, there'll of course be one case in which there are no valid insertions, right? So we'll check all the numbers from 1 to 9 and there will be no valid insertions. So I'll just show that here. Say for example, we inserted 2 here and over here 1, 2, 3 can't go, 4 can't go. We'll insert 5 here. Then what? We'll insert, can we insert 6 here? Yes, we'll insert 6 here. Okay, here in this square, you can't insert any number from 1 to 9. They'll all be invalid, right? So what do? We will backtrack. So we'll go back to the last square. We'll change this number to 7 and check. Then 8 and check. Then 9, right? So we'll backtrack and we'll call the function all over again. So if this, oh sorry, here it should not be returned true, right? It should be actually be returned false. So after I go inside the for loop, if there are no numbers which can be inserted, it will return false. Now, if it returns false, it will backtrack, right? Hopefully, you know the recursive functions are stored in a stack. So the uppermost function will be hopped out of the stack and we'll go to the function after that. Basically, we'll backtrack. So we'll go to the last square and we'll again go inside this for loop. We'll insert another number. Okay, first of all, we'll set it to 0, right? We'll check, we'll do board row of column is equal to dot. So dot basically means that it's empty. So we'll go back to the last square. we'll first set that to a dot, showing that it's empty. Then we'll again go inside this solver function. We'll find the empty square and do all this all over again, right? Hopefully you guys understood how this works. All right, now we have to call this function. We didn't call the main function. So we'll just do solver of word. Hopefully the indentation is correct. No, it's not correct. It should go inside. Okay, so we actually made some bugs here. The first bug is that over here, J should be, it should be in range. And then our is valid function, V should be caps, okay? Now, apart from that, as I said, we have to compare. Now, here we are inserting numbers, right? But we have to convert that into a string because we'll be comparing it to a string, right? Like not as integers because our input is like that. So let's run this and see. Let's see if it works. And it works. Let's submit. And it got submitted. So that's basically how you solve this problem. If you have any doubts, do leave them in the comment section down below. I'll be happy to answer them. Now, I know at first this might seem a bit complex, but once you understand it, it's actually really, really easy. All right, so that's it for this video. I'll be leaving a link to this code in my GitHub repository. Like I'll be leaving the link down below. All right, so don't forget to like and subscribe, and that's it. I'll see you next time. Bye.